Good morning. In this lecture series, we see about the general procedure and application of software engineering, software in FEA. So the first of all, so we have to discussing the what are the general steps we have to use in the finite element analysis, and especially we have to using for the different types of application in finite element analysis. So as we know that the finite element analysis is a powerful numerical techniques that will be transforming the modern engineering and design analysis. So as we know that in this that so first of all the finite element analysis is a sophisticated the numerical techniques that resolves the complex engineering and physical problem by the breaking them to the smaller and simpler part of is called as a finite element analysis. So in this revolutionary approach, the enabling the engineers to approximate solution for the differential equation across the structural, thermal, and fluid and the electromagnetic analysis. So the first step we have to generalizing the geometric representation and discretizations. As we know that is a CAD is a model creations and misgenerations and quality assessment. So the what is a CAD modeling creations? They begin with the precise the computer-aided design model and that accurately represents the physical geometry for your component or system. So the mesh generation, the discretize the geometric into the mesh into the finite element and typically triangle or quadrilateral in the 2D and tetrahedral, hexagon and the 3D connecting with the nodes. And the quality assessment, the mesh quality element size is critical the affect the both accuracy and computationally cost and requiring the careful balancing between the precise and efficiency. So the step 2 is the element formations of the assembly. So first of all, the element equations. So what is the element equations? They're based upon the material properties and the governing physics such as the stress-strain relationship for the structural analysis or heat transfer equation for the thermal problems. So the mathematical derivations utilize the advanced method like a principle of virtual work Galerkin method to derive the stiffness matrix that can be describe the element behavior. So the global assembly, the assemble the all the individual element equations into the comprehensive global systems of the equations, the representing the entire model of the behavior. So applying the boundary conditions and load. So the constraint the define definitions, the specific constraints such as the supports and the fixed beam to prevent the and release the rigid body motions. So it can be simulating the load applications, the applying the external force, pressure, thermal loads, and other relevant conditions. The precisely at the node or crossing the all the surface and while design checking the proper boundary conditions or establishment enhancing and ensuring the simulation result and accurately reflect the real world physical behavior. So what is the step 4 is the resolving the system equations. For resolving the system equation, the first of all, so we have to frame the equations and the equation formations and the computational process and the accuracy balance. So generally the large system of the linear and non-linear algebraic equations is can be represent the unknown node value of like a displacement and temperatures. The computational process, the leveraging the powerful computational revolutions to solve the model with the thousand millions of degree of freedom of efficiency, and also the accuracy balancing the solution accuracy improving with the finner the mesh but requiring careful management and the computational time source. So the last one is a post processing. After the result visualizations, the transformation raw numerical data into the inequality counters, plots, and deformation shape and stress distributions or temperature field or comprehensive analysis. The critical region identifications, the point-to-point area of the concern surface as a high stress concentration and the potential failure points and the thermal hotspot require the design attentions. So while going the design optimizations, the leveraging the simulations inside the refine the design and enhancing the safety margin and reducing the material usage and improving the overall product performance. The popular finite element applications of these softwares. The first one is as a ANSYS mechanical, abacus, and a COMSOL multi physics, and a calcium and Elmer's FEA. So the first one is ANSYS Mechanical, the aerospace and automobile and manufacturing for the complex engineering challenges. And Abacus is an industry leading and software futures advance the non-linear and dynamic analysis and the capabilities of the complex material and the contact interactions. And the COMSOL multiphysics, the flexible platform seamlessly integrating the FME and with the numerical methods for the sophisticated couples physics problems and the multidisciplinary analysis. The open source solver is the compatibility with the Abacus, the input file, offering the robust capability suitable for the both academic and research in industrial applications. The Elm of FEA is an open source, the multi-physics software is a developed the CSC Finland supporting and the comprehensive thermal structure and the fluid dynamic systems. So overall summary of this topic is we have to classify the system procedure and the application of software and engineering field. So while coming the engineering field, the structural analysis and the thermal analysis and fluid analysis is very much important, and the applications are these are the modeling, meshing and the material property assignment and the analysis and the post processing. Thank you.